Alright gang, here we go. So this is Chem 2 Unit 4. We're talking about stoichiometry applied to solutions. Alright, so this is the last bit of the chapter. Congratulations, you've made it. So we're just kind of bringing everything we've kind of talked to just to a close and kind of wrapping things up here. All right. So stoichiometry, remember all of chapter 3, all of unit 3 was all about stoichiometry. We did we read out reactions and figured out how they reply to each other. So now we're going to do the same thing, but we're going to do it to solutions. So really this is just putting another tool in your tool belt. And so we're going to use these stoichiometries. Okay, and this is just kind of their tree here that kind of tells you how to use them and what kind of ratios they can help you get to. So remember, so we go from here's our moles of A, moles of B, and we can get to masses of both of them, and then we can use our molarity. Remember, molarity is equal to the moles of the solute per the liter. So we can use the molarity to convert moles of whatever it is we're talking about either into volume or into molarity, and in order to do that we just use this ratio. If we're trying to find molarity, we simply divide by the volume. If we're trying to find the volume, we simply take our moles and divide by the molarity. Okay, and pretty easy. Just follow your units. Dimensional analysis is the key. We'll do a couple practice problems coming up. Now there's a new term or a new system that we need to talk about. In Chem 1 we did several titrations, so this should look familiar to you. But just as a quick recap, titration is an analytical technique. So this is a technique that we're going to use to actually calculate or analyze a solution. All right, and so what you do is you start with something that you don't know. Okay, you start with a solution and you're like, I know what this is, but I don't know what the concentration is. Okay, and so so in this case, in their little diagram here, they have their Erlenmeyer flask and they're adding 20 milliliters of an acid. Now they don't know the concentration of this acid, but they've added it to this flask and they're going to use titration in order to figure out what the concentration is. Then they add an indicator. Okay, in this case, I think they're using phenolphthalein. So they use this indicator that's going to change color when your solution goes from being acidic to basic, right? Because when you're acidic, you've got more acid in there. Once you're basic, you've got more base in there, right? So then in their burette, so this is this part up here in their burette, they're going to add a standard NaOH. Now this term standard, what that means is that it's a known concentration. All right, so this is a known concentration. All right, and they're adding that known concentration of the base into your Erlenmeyer flask. All right, now the trick is with burette is that they always read backwards. Okay, so your initial volume reading is going to be up high, and so at the top is going to be 0, and as it goes down, you're going to, so it's going to be like 1, right, and 2, and 3, and so as you go down, you're reading how much you've added to your Erlenmeyer flask down here. Okay, now as you're adding this base, right, so let's just assume that we've got hydrochloric acid, right? I wonder if this is what, no, this is, so let's just assume we have hydrochloric acid in this original Erlenmeyer flask over here, and we're adding NaOH. This is kind of the quintessential example. We know that since this is a metal hydroxide reacting with the acid, we're going to be forming water and a salt, or salt and water, and this is, right, so we're going to be making those two things. So really what's happening is that as long as there's hydrochloric acid moles left in our original solution, we're going to have a neutralization reaction occurring. So we're going to add the base in here, and this base is going to drop in here, and then it's going to, once all of our hydrochloric acid has been used up, it has been neutralized. And once it's been neutralized, our solution will go from clear to pink. And that's because of that indicator we added in step 2. Right? So now our solution is pink because we've added as much base as acid we started with. Now, when that color change occurs, that's called the equivalence point. Okay, equivalence point. So really, you should focus on the equivalence point. You should think of this equal part, right? Equal. So that really means that you're at equivalent. Shoot, I can't even spell it. Equivalent number of moles. Okay. Because if you think about it, when you're adding your NaOH and your HCl, you're going to reach your equivalence point when the moles of the base that you added is equal to the moles of the acid you started with. You started with a number of moles of acid in this solution. You don't know how many moles of acid you started with, but if you can figure out how many moles of base it takes to neutralize it, then that's way you can tell how many moles of acid you started with. And that's kind of the basis of titration. All right? So here's kind of the steps of what you're doing. You're starting with a volume of a standard solution needed to reach the equivalence point. So that's this volume here, from here to whatever this ending thing is here. So you're starting with that volume. You're going to use the molarity of the standard solution, of that NaOH in this case, to find the moles of the standard solution. So you can figure out how many moles of the standard solution you added. Then from your balanced chemical equation, you can figure out how many moles of your unknown you had, and then use the volume, and specifically this is the original volume, right? The original volume of unknown solution to find the concentration, right? So in this case it would be 20 milliliters, all right? So the solution of known concentration is called the standard solution, and you use that to determine the unknown. When when the reaction is complete, you're at the equivalence point. Okay, and for the most part, it's going to be equal to what's called the endpoint. The endpoint is the special word we use to represent the color change. Now, the color change occurs at different values depending on what indicator you use. Earlier, when we talked about acid and bases, we talked about a universal indicator that was a mix of all different indicators. When we get to our acid-base unit for realsies second semester, we're going to spend a lot of time talking about different indicators. But specifically, our equivalence point is when the reaction is complete. Our endpoint is when the color change occurs. All right, so we're going to do some practice problems here. Here we go. All right, so it says how many milligrams of sodium sulfide are needed to completely react with 25 milliliters of a 0.01 molar aqueous solution of cadmium nitrate to form a precipitate of cadmium sulfide. So first step, anytime you're approaching any stoichiometry problem, which is what this is, we're going to first write out our balanced chemical equation. All right, so we got sodium sulfate, sodium sulfide, so we got sodium, right, and sulfur. Sulfur has a charge of 2 minus, sodium is plus 1, so we need 2 sodiums, all right, and this would be aqueous, all right, is reacting with aqueous cadmium nitrate, so that's CdNO3. Now, cadmium is one of our transition metals we have to memorize. It has a charge of 2+. Nitrates are polyatomic. That has a charge of -1, so we need 2 of those, and it tells us it's aqueous, right? All right, so those are our reactants, and it tells us one of the products. It tells us we're going to form CdS, cadmium sulfide, solid. All right, so that's one of them. So it makes it pretty obvious that this is a metathesis reaction, a double replacement, right? So the other product would have to be NaNO3, right? And so we got to balance this. So we got 2 sodiums over here. We need another sodium. And then sulfur, sulfur, cadmium, cadmium, 2 nitrates, and now we've got our 2 nitrates. So life's grand, all right? Now, the trick is now we got a balanced chemical equation. We need to find how many milligrams of sodium sulfide we need to completely react with this volume and concentration of cadmium nitrate. All right, so we're starting with cadmium nitrate. Now we need to figure out, we're going to go from molarity to milligrams. Okay, so what we're going to do, remember, when we have this symbol here, this 0.01 molar, that's the equivalent of saying you have 0.0100 moles of CdNO3 to 1 liter, right? Those two things are saying the exact same thing. So we can say, well, we have 0.0100 moles of CdNO3 2. Why did I suddenly? NO3 2, right? CdNO3 2 for every 1 liter, right? Now we need to get rid of our liters, so we're just in moles. So we'll multiply it by our volume. Well, it says it's 25 milliliters, so that would be 0.025 liters. Okay, so now our liters cancel, so we're just in moles of cadmium nitrate, and now we need to get to grams or milligrams of sodium sulfide, which is this guy. So now we need to use our mole ratio to go from moles to moles. Well, so here we go. So we've got for every 1 mole of CdNO3 we get 1 mole of Na2S, right? So that's a 1-to-1 ratio, all right? And now we need the molar mass of sodium sulfide, right? Because we're going from 1 mole of Na2S to grams of Na2S. All right, so we've got 1 sodium, right? 1 sodium, and two sodiums and 1 sulfur. We're going to add those guys up, right? So sodium is 22.99, right? So 2 times 22.99, and sulfur is 32.07, 32.07. So we're going to add those guys up. So 2 times 22.99 plus 32.07, we get 78.05. All right, so we'll put 78.05 grams down here. So 78.05 goes here. All right. All right, and then, but it asks for milligrams, so we're going to do one more step where we convert from grams. We know for every 1 gram, we have 1,000 milligrams, right? Because it asks for milligrams. And so now we're good to go, right? So we take our 0.01, and we're going to multiply it by the 0.025 to get rid of the liters, divide by 1, multiply by the 78.05 to get to molar mass, and then multiply by 1,000, we get 19.5. All right, and our unit, so here's my pen, so it would be 19.5 milligrams of Na2S. All right, so there's your answer there. All right, and so 19.5B. Nice, we did it. Okay, we're not going to do practice exercise 2. It's essentially the exact same thing. All right, but we are going to do practice exercise 1. All right, and not exercise 2 because it's essentially the same thing. So it says, what is the molarity of an HCl solution if 27.3 milliliters of it neutralizes 134.5 milliliters of 0.0165 molar BaLH2? So this is essentially a titration problem, okay? We started with an unknown HCl solution. We started with 27.3 of milliliters of this HCl. We don't know what the concentration was, and we know that we added some sort of indicator, and we know when we reached equivalence point we had added 134.5 milliliters of this barium hydroxide. All right, so first step we're going to do is we're going to write out our neutralization reaction. So we're going to have HCl, okay, our hydrochloric acid, this is aqueous, and it's going to be reacting with our barium hydroxide, BaOH2, and this is also aqueous. And so this is a metal hydroxide and an acid, so this is going to make water, H2O, and then a salt, and H2O is a liquid, and then a salt. So in this case it would be Ba is our metal, and then Cl2 would be the salt we're making, right? All right, now we have to think to ourselves, well, is it balanced? So 1 chlorine over here, 2 chlorine, so we'll throw a 2 over there for the chlorines to be balanced. So that means we're also going to need, right now on this side we've got 1, 2, 3, 4 hydrogens, so we need a 2 right there. And so let's just double, so 1, 2, 3, 4 hydrogens, 1, 2, 3, 4 hydrogens, 2 chlorines, 2 chlorines, 1 barium, and 2 oxygens, 2 oxygens. Yep, so we're balanced. Okay, so then it says, what is the molarity of HCl if we start with this volume, if it neutralizes 134. So we need to figure out how many moles of base we added. Remember, because when we reach equivalence point, we're going to be at the point, remember, so when we're at the equivalence point, really what we've said is that the moles of the acid is going to be equal to the moles of the base, right? Because that's the whole point, is that they've equalized, right? Moles of acid is going to be equal to the moles of base. They've equalized with one another. So the moles of the barium hydroxide, this specifically the hydroxide that we added, is going to be equal to the moles of HCl. So really we just have to convert that to that, right? So we got to figure out how many moles of barium hydroxide we started with. So once again, we're going to use our little cheat here. We're going to say, well, that's 0.0165, and molarity is the same thing as saying moles per liter. So we'll write moles barium hydroxide, okay, for every 1 liter, okay. And we need to get rid of our liters. So you should be noticing a pattern from the last problem here. So this is 0.1345 liters, right? So our liters cancel, okay? And then we're going to convert it to moles of our acid, right? So we put moles of BaOH2 in the bottom and moles of HCl in the top. And so we get, it's a 2-to-1 ratio, so we put a 2 with the HCl and a 1 with the barium hydroxide. All right, so now we're in moles of HCl. All right. Okay, so that's that. So now so once we plug that in, we'll have moles of HCl. So we'll say 0.0165 times 0.1345 times 2, and we get 0.00. Yeah, okay. I did it earlier and I got it. I realized I did it a different way. So we should still get 0.0044385. All right, 0.0044385 moles of HCl. So this is the moles of HCl that we had in our solution. Well, we need concentration. So remember, concentration is moles per liter, so we'll take our moles. So the concentration of our HCl solution will simply be equal to the moles of the HCl, so that would be 0.0044385 moles. And we're going to divide that by the volume that we start with. But remember, it has to be in liters, so it would be 0.0273. Okay, so we'll take 0.004385 divided by 0.0273, and we get 0.16258, and this one, everything's got at least 3 sig figs, so it'll be 0.163 molar. 0.163 molar HCl. So we started with, so now we know that this unknown solution that we started with, that we have 0.163 molar HCl in our Erlenmeyer flask when we started our titration. Okay, and that's it for the chapter. Congratulations, you made it all the way through. Very proud of you. Do your homework problems, get ready for your upcoming quizzes and exams. Let me know if you have any questions.